Good afternoon, everyone. Today I will present a detailed analysis of the paper titled "A Performance Analysis of Security Protocols for Wireless Sensors Networks," which conducts an empirical evaluation of multiple cryptographic security protocols under the constraints of wireless sensors networks, or WSNS. This paper stands out for its practical emphasis on real-world development challenges and contributes meaningfully to our understanding of lightweight security solutions in embedded systems. I will introduce it in 5 parts. The first part is summary of the paper as one of the key technologies of the IoT and embedded systems. Wireless sensors networks are widely used in military detection, environmental monitoring, medical health, and other fields. However, since its nodes are usually deployed in remote or dangerous areas with high energy consumption constraints, low computing power, and storage limitations, they face severe security challenges. This paper is dedicated to systematically evaluating the performance of various security protocols designed for WSN and finding the best protocol architecture that can ensure security and maintain communication efficiency under resource-constrained conditions. The author analyzed the performance of lightweight protocols such as TinyScan, MiniScan, LEAP, SPANS, and TinyPK on multiple performance indicators through experimental simulation, and compared and discussed the problems they may encounter in actual development, and put forward adaptive improvement suggestions. This study helps to provide a theoretical basis and practical reference for the design of future WSN security protocols. The second part is key problems addressed. It mainly solves 5 problems. The first one is security protocol adaptability under resource constraints. WSN nodes are usually equipped with low power processes, limited RAM and ROM, and non-replaceable batteries. Traditional security protocols are not suitable for WSNs due to their high computational overhead. The second one is balancing diverse security requirements, including data encryption, authentication, integrity verification, and anti-tampering capabilities. These functions often have mutual constraints in lightweight design. The second one is protocol communication overhead issues. Additional data in the communication processes, such as message authentication code MAC, will increase transmission delay and energy consumption, which need to be weighed. The fourth one is synchronization issues and inter-node collaboration challenges. Some protocols have high requirements for time synchronization and are not suitable for asynchronous or large-scale distributed networks. The fourth one is evaluation and selection issues. This is a lack of unified and protocol evaluation standards and environmentals, and a lack of comprehensive understanding of the performance differences of protocols. The third part is methodology used for protocol selection and grouping. The author selected 5 mainstream WSN security protocols, each of which represents a different encryption strategy and architecture design, including symmetric encryption, public key encryption, and authentication mechanism based on time synchronization, TinySec based on symmetric encryption algorithm. It is simple and easy to implement and widely used in TinyOS environment. MiniScan provides stronger data integrity protection and replay attract protection. LEAP adopts multi-key mechanism to achieve flexible authentication and communication between nodes and groups. SPANS consists of SNEP and mu Tesla with high security. 10APK introduces public key infrastructure to improve security but bring high resource costs. Mechanism, evaluation, dimensions, and indicator design. The first one is memory overhead. The adoption of secure protocols can significantly affect RAM and ROM utilization on constrained devices. The second one is CPU circle utilization. CPU utilization was measured during protocol handshakes and message exchanges. TLS 1.3 demonstrated improved handshakes efficiency, reducing CPU circle consumption by approximately 20% compared to TLS 1.2. The third one is communication data overhead. Secure protocols lead communication overhead via handshakes, key exchange, and certificate transfers. In our measurements, TLS 1.2 introduced up to 18% data overhead per message, while TLS 1.3 reduced it to around 11%. The fourth one is energy consumption model. Using consumption tools, we modeled energy consumption across protocol configurations. Frequent handshakes and QoS acknowledgements significantly increase the power draw. Next is experimental platform and simulation method. The author uses TOSSIM and Simulation test platform, writes a practical logic in combination with NENC language, runs the protocol under different network topologies, and records and counts the above performance indicators. The test scenario covers different density developments of 20 to 100 nodes to ensure the universality of the results. The fourth part is evaluation of results and findings. Divided into two parts, the first part is performance comparison. MiniSec provides a good balance between energy efficiency and security and is recommended for middle-sized developments. TinySec, it has minimal memory and communication overhead and is suitable for nodes with extremely limited resources but lacks a strong authentication mechanism. The multi-key mechanism improves the flexibility of nodes communication and platforms will in group communication. SPAN's new Tesla solution can effectively provide broadcast authentication but requires a strict time synchronization mechanism. TinyPK, although the introduction of the public key mechanism improves security, its large-scale computing and communication burden makes it unsuitable for resource-constrained nodes. The second part is comprehensive conclusion. Currently, no protocol can outperform other protocols in all performance dimensions. Security protocol design must be customized on demand and selected based on factors such as network density, node type, power consumption, tolerance, and so on. Before actual development, it is recommended to combine network simulation tools. The fifth part is relevance to the course topic. There are 4 main points. The first one is basics of network security. Introduces common technologies such as symmetric encryption, public key encryption, MAC, and time synchronization. Authentication involves authentication mechanisms, key management, and encryption algorithm selection issues. The second one is embedded system security, focusing on how resource-constrained devices can achieve secure communication is an important part of the embedded system design course. It has protocol guiding significance for the design of security modulars in low-power systems. The third one is Internet of Things Security Architecture, discusses the development of security protocols of different scales in IoT scenarios, especially for sensors networks, intelligent transportation, and environmental monitoring systems. The fourth one is system modeling and simulation. Mentions the simulation evolution processes of the protocol, involving the use of tools such as TOSSIM for system modeling, data recalls, and resource analysis. That's all. Thank you for your listening.